we presented this machine learning for physical layer communications, and the outline of our presentation goes like this. So starting from the physical layer, traditional physical layer communication system that is made of, separate blocks from the transmitter to receiver, as you can see. The main goal is to be able to decode with minimum probability of error the transmitted symbol at the receiver. Now, so why do we need machine learning in wireless communication, 5G and beyond? First of all, is communication versus optimal solution. As you can see in the traditional communication systems, each block is being optimized individually. And that is actually cumbersome. And then the mathematical model versus system imperfection because of the non-tractable mathematical representation of some of these signal processing blocks. And then the algorithms, the traditional algorithms are inefficient due to the computational complexity of such algorithms. And of course, there is increasing expansion of the network as we move from full 5G to 6G and beyond. So a typical way of learning end-to-end communication is using autoencoder. As you can see, the first block represent single one transmitter and one receiver system, and then we can extend this into multiple antenna scenario where you have a bunch of antennas at the base station, and then you have multiple users at the receiver end, as you can see. Now, what are the challenges of this machine learning approach? Of course, that unlike in deep learning community where there is availability of training data set, we don't have that in the communication domain. It's still an ongoing research field. And then we require model-oriented loss function architectures where we don't have to rely basically on just using a deep learning framework as is traditionally used by stacking layers. And then we have to look at the complexity of the neural network of deep learning architectures, which has actually received less attention within the communication community, unlike the machine learning or deep learning community. So one of the ways of actually dealing with that is to use the model-based solutions, because we do have them, because communication engineering is actually a very mature field where optimization solutions have actually been available. So we can use those solutions as training levels, and then we use machine learning approach to approximate such solution, as you can see in this diagram. The next thing is to combine the model-driven approach and the data-driven approach by exploiting the expert knowledge using the mathematical representations of such optimization problems. So one of the ways of actually dealing with that within the deep learning communication community is to do model simplification, because at the end goal is to actually deploy such deep learning frameworks into end device. So the traditional approach of model simplification is pruning and drop out, where the layers or neurons are actually shot or dropped during training and inference. So, and then what has actually not been reported in literature is actually structural factorization, where we can play around with the layers and then the neurons during both training and inference by introduction of some ingenious approach. And then weight quantization. The weight quantization is representation of the layer weights with low bit representation. So some of these approaches are actually being used in available in deep learning frameworks, but beyond a kind of a moderate bit representation of 16-bit, 8-bit, and 4-bit, lower bit like a binary bit has actually not been explored within the communication community. So, and then there is hybridization, weights, activation, and presentations, where the weights and activations are presented by, a combination of full precision floating point and then the binary bits. So we extend this approach to how it is done in MIMO signal detection. In MIMO signal detection, the whole of the communication system can be represented like this. We have a transmitter side. At the transmitter side, we do pre-coding where, the transmit symbols, transmitting a transmitting pre-coding or beamforming vector is designed to pre-code the transmitting vector before transmission, because we don't have control over the channel, but we do have control over the transmission symbols before being transmitted. So some of the classical approaches that I use are block level pre-coding, and then optimization-based square coding, and then THP pre-coding, and linear, which is zero forcing and minimum mean squared error. So at the receiver side, we also have these equalization approaches that I used to decode the signals, transmitted symbols. So we can replace the pre-coding problems here, pre-coding solution, with deep learning framework to learn some of the parameters that would actually estimate the pre-coding matrix or pre-coding vector. The same thing at the receiver, we can either approximate or design a deep learning framework that would do some of this optimization based on these optimization problems. So this is one of the ways that we have of doing structural simplification, where instead of doing pruning or drop out, what we were designing layers with by the introduction of some kind of a scaling function, and the scaling function is represented by this beta, where the beta is monotonically non-increasing function that would be applied to the weight, such that during Ford Powers computation, that this function will scale down the values of the weight, such that the significant weights are retained and non-significant weights are dropped during training and inference. So as we can see, by removing significant weights, non-significant weights, the dimensionality of, or the complexity of the deep neural network has actually been reduced significantly, as you can see in this diagram, that by dropping out 50% of the weight of the neural network, we still achieve a very good performance. The next thing is we try to explore the extreme bit quantization using a binary representation to represent the weight and activations. So this is a symbol level pre-coding approach. So we're trying to minimize the transmit power here, subject to the inequality, subject to the quality of service, or SNR constraint. So with this, instead of the normal way of actually doing stacking layers, so we are now trying to build a neural network framework that would take care of the constraint optimization problem like this one. So we can represent this one as this problem, and then after some mathematical transformation, we're able to represent, where we introduce the concept of a proximity barrier function that would enroll this mathematical representation into unconstrained optimization in a way that we can actually design layers that would learn some dual variables or Lagrangian variables that would be able to minimize the function. So this is the Lagrangian model as represented by the Lagrangian model equation. And then this is the unconstrained or deep unfolded version of the unconstrained optimization problem, where we learn the dual variables that would minimize the power, the transmit power. So, and this will give us an avenue, or will enable us to use the loss function directly as this, using Lagrangian regularized function as this. So how the weight is actually being quantized, we use binary quantization using this expression, and then we introduce another quantization technique, which is ternary, using three-stage quantization instead of two-stage quantization as in binary. So you can see this is a typical way of how the weights are being quantized based on these expressions. So one of the benefits of this kind of approach is that reduction in complexity, and then there is memory efficiency. Of course, if you're doing online training, we should expect to do the online training on a very resource-constrained devices. So and it's hardware friendly because of the reduction in memory consumption. So some of this, the results, numerical results is here. As you can see, we draw the average transmit power versus SNR. So the approach, the data-driven approach of learning-based recording scheme, is almost close to the optimal solution. And in terms of complexity, it is 40% less than that for the full precision learning framework, and then for the binary or quantized learning framework is over 50% reduction in complexity. So you can see the memory utilization. We have achieved about 21% reduction, memory savings for the binary, and then for the ternary, 13% or 13 times memory savings, as opposed to the full precision network. Now, moving to the deep learning framework for physical layer security. This is a typical example of, as you know, 5G and beyond communication system is expected to, or are expected to support ultra dense connectivity due to the massive, due to the increase in wireless devices and widespread of IoT devices. So one of the challenges of this is kind of security, because of the increase of this massive connectivity. So the network is actually prone to the potential attacks. So an example of the attack is where you have the legitimate user sending signal to the receiver or sending information to the receiver, and then you have a eavesdropper or a spoofer trying to spoof the transmit data. So a typical way of solving this problem is using radio frequency fingerprinting. Is an emerging technology that uses the inherent characteristics of the transmitter, of the characteristics embedded in transmitter waveform to identify or characterize the transmitting device at the receiver. So this is a typical representation layout of the RF fingerprinting, where we have the signal processing block comprising of some of the hardware. And then this is the experimental testbed, where some methods are used for fingerprinting. Some of the traditional approaches are model-based approach, statistical-based approach, transient-based approach, and wavelet-based approach. So I'm giving an example, a typical example of transient-based approach, where the transient part of the signal is actually being characterized and used to extract the feature of the transmit waveform that would be used for device identification and feature device identification. So going beyond this, we can apply learning approach to be able to represent some of these hardware impairment in this. Okay, now it has so many applications ranging from smart healthcare, smart transportation, smart agriculture, smart education, and things like that. But there, of course, there are challenges. There has actually not been a very robust method of hardware imperfection. So it's actually a very active research area. Impact to receiver hardware, vulnerability to blind attacks, impact effect of multiple path propagation has actually not been studied. And then simulation reality gap, there is a huge gap between the experimental test bed and then the theoretical theoretical way of dealing with such imperfections. So we are proposing to build a learning framework using autoencoder that would encode the transmit signals, and then we use the machine learning approach to build the hardware impairment to learn the hardware impairment. Not only using the machine learning approach using conventional way, we're trying to see how we could explore the expert knowledge, the mathematical representation, so that we build a very sound theoretical foundation where we can actually apply machine learning to learn some of the physical RF physical hardware impairment. So it shows an example where you have a legitimate user and you have the dropper channel, and then we use this learning layer to extract the features from the signal received from the channel, from the dropper channel and from the legitimate user channel. And then we concatenate this and apply that to the, we design a decoder, learning a decoder using, deep, dense layers. And we use, different loss function for the events dropper and for the legitimate user. So for the events dropper, for the legitimate user, we try to maximize the probability of decoding the transmit symbols. And then for the events dropper, we try to we try to minimize the probability that he could decode the transmit signals. Thank you.
Hello, my name is Mateen Ashraf, and currently my area of work, research work, is about beam farming, specifically in ISAC-based systems. But generally in modern wireless networks, we can say that beam farming usually is typically can be considered to be divided into beam selection, tracking, and beam alignment. And this is usually in modern networks can also be achieved through coordinated beam farming by having coordination among the base stations, or by utilizing some other newly developed technology such as IRS. And then the idea of the beam farming is basically to improve the quality of the communication systems by estimating the channels and using the information of the estimated channel, and then directing the beam towards a proper direction so that the better quality channel can be observed toward the intended user. So this is the basic idea of the beam farming techniques. And there are different challenges that are involved in while performing the beam farming, and these are basically due to the model-based approaches that are basically used in optimization techniques, where the objective function or the constraint functions are actually converted into some approximations, which results in performance losses due to a compounding effect of over multiple iterations based algorithms. And also because it has higher computational complexity due to a higher number of variables in, for example, massive MIMO system, or a higher number of elements within the RAS-based systems. And moreover, the solution that we obtain during these techniques may not be applicable for the future time slots, because the information over which using the information that is used to approach to the solution may have been overridden or maybe destroyed. I mean, historically not true anymore. So there is a need to adopt to other methods such as machine learning based methods. And the main attraction involves because they can have adaptive solutions for changing environments. And if we have neural network, then we can actually obtain the solution pretty quickly based on a learned network. And then the other important thing is that while the conventional optimization techniques, they rely heavily on model-based approaches, these machine learning approaches can also use the non-model based approaches as well. But on the other hand, it also has some limitations. For example, the training data is not most of the time not available, or not available in a form that can be used for these approaches. And then the performance guarantees which can be made for conventional optimization techniques may not be possible to claim such performance guarantees for machine learning based solutions. And also one other issue with this scheme is that how to choose the hyperparameters within the networks, neural networks or some other networks. So specifically in beam farming in ISAC systems, so we also have the conventional wireless network system based beam farming schemes, such as beam farming training for downlink and beam farming training, beam training for uplink. But there are other techniques also which try to optimize the beam direction based on the information that is provided by the by having the sensing capability within the network. And then using that information, we can actually improve on the channel estimation quality by using some channel prediction techniques based on the sensing information that we have obtained over the network. And then learn the beamformer as we go along the time, and then also predict for the future time slots. So in a way, circumventing the drawback that we had for our conventional optimization based scheme of non-causality. We can cater that if we have these schemes. And then if we compare what are the challenges that we can see in future for ISAC based beamforming schemes. So most of the solutions that thus far has been proposed are based on single time slot based systems, but usually we really want to have a long-term based solution, and where the optimization is performed over some more complex combinations of different objective functions together. So then it becomes a big problem for conventional mathematical based optimization schemes, since then the properties needed to solve them may not hold anymore. So then the data driven approaches or machine learning based approaches, they become more attractive. And also some other hardware impairments and imperfect information availability of the system also causes these similar kind of problems. So we expect that the machine learning approaches will actually play a very vital role in ISAC based beamforming system as well. So this ends our presentation. Thank you for listening.